Let me continue my discussion with crystal structures. We are discussing about the silicate structures. We have discussed the seed silicate structures, and now let me go to another topic in the same on the same subject, that is the crystal structures of silicates and silica. To start with, we will look at the polymorphic forms of silica. Okay. Silica SiO2 is basically composed of silicon oxygen tetrahedron, and we have seen how this silicon oxygen tetrahedron can be combined with other cations and form a series of different silicates. But pure silica is also a very important raw material for the ceramics, not only for the traditional ceramic group, but silica sometimes is also important for advanced ceramic products in combination with other oxides. So, let us try to look at silica is a very complex material in some way, because it has many different polymorphic forms. Polymorphic forms means it has different crystal structures. Okay. So, if you want to have a look at the different crystal structures, first of all let us try to understand what are the different polymorphic forms pure silica may have. There are on the low temperature side, you have what we call high quartz, or sometimes called beta quartz, and the still low temperature you have a low quartz. So, these are the low temperature regions, and then these are high temperature, and the highest temperature is here. So, you have low quartz, which is alpha quartz, sometimes called alpha quartz, and if you heat above 573 degree centigrade, which is a very specific temperature, around above this you have a high quartz, okay, or sometimes is referred to as beta quartz. There is a density change, volumetric change. So, it is a kind of problem transformation for the industry, because whenever there is a volume change, there is always a tendency of cracks. So, making a densified material with pure silica is quite difficult. There are techniques by which one can avoid that, but otherwise most of the time in the industry this transformation is actually a very problematic phenomenon. There are different kind of transformation in the whole gamut of different phases, low alpha quartz, beta quartz, then that beta quartz goes to high tridymite. Okay. High tridymite is another name of same composition, chemical composition SiO2, but with a different structure. Then if it is heated to still further, this transformation takes place around 876 degree centigrade, and then this around 1470 this goes to Crystallite, and then beyond that of course silica melts at around 1710 degree centigrade. Now, then this high tridymite, once again if you cool below about 160 degree centigrade, you will find another phase forms, which is called beta, a middle tridymite, and still below about 100 degrees, around 100 degrees centigrade, it goes to low tridymite. Here also the crystallite goes to a low crystallite phase, which is different from the high crystallite, but much lower temperature, 270 degree centigrade, okay, around 270 degree centigrade. In fact, these transformations are not always a thermodynamic transformation, some of them are different forms of transformation, I mean not always an equilibrium transformation. there are some non-equilibrium transformations also. Let us try to look at it. There are two types of transformation have been indicated in this table. One is called displacive transformation. Okay. This is called displacive transformation. This transformation from high quartz to high tridymite is a reconstructive transformation. Then another reconstructive transformation takes place from high tridymite to high cristobalite. When these are cooled, this goes to the low cristobalite phase through a displacive transformation. Once again, high tridymite, when it is cooled, it goes through a two different displacive transformation, one at around 160 degrees, another at 105 degrees centigrade. Let us try to understand what is the difference between a displacive transformation and a reconstructive transformation. We will discuss part of it later on in our topic on phase transformation. What is the mechanism of phase transformation, how one particular phase can transform to another particular phase. Phase in this case we are basically referring to two different crystal structures. One crystal structure is changing over to another crystal structure as a function of temperature. So, whenever the phase transformation is taking place, a particular arrangement of atoms is getting changed to another geometric pattern of the atomic arrangement, and therefore, there is always a what we call the mass transport. A particular ion is moving from one position to another position, okay, and therefore, it can go through a process of what we call a nucleation and growth phenomena. If you talk about phase transformation, there are many mechanisms of phase transformation. One common phenomena which takes place is nucleation and growth phenomena. Initially, a small nuclei of a different crystal structure nucleates, and then more and more atoms join that particular structure and continue to grow. So, that is what we call the nucleation and growth phenomena. It involves a long range movement of a large number of atoms, okay, by step by step manner. So, it is a time dependent process. It is not only a temperature dependent process, but also a time dependent process. So, it has a kind of isothermal reaction. So, it nucleates at a particular rate and then grow at a particular rate. So, as time proceeds, more and more transformation takes place, and you get 100% transformation only after allowing sufficient time at a particular temperature. There may be another mechanism by which the similar phenomena can take place. One structure is changing over to another structure, but it is time independent. It does not take very long time, but almost instantaneously through a cooperative movement of a large number of atoms, simultaneous movement of large number of atoms, one particular geometry changes over to another geometry, and that is time independent, or sometimes it is called athermal process. The previous one, the time dependent process, is called isothermal process, and the second one, which is time independent, is sometimes called athermal process, and these two distinctions of phase transformations are very well known in material science, including ceramics. So, when we are talking about these two transformation here in reference to transformation of silica, then we have a displacive transformation. This is actually a time independent phenomena. That means, it is a very fast process, okay, and that is a thermal process, and also it is sometimes another way of looking at it is it is a diffusionless transformation. Okay. It is a diffusionless transformation, that means no long range movement of atoms. it is some kind of a shear movement, a small distance of movement by atom of the atoms, but cooperative movement of atoms can change over from one geometry to the another, and that is what we call the displacive transformation, and it is extremely difficult to quench this transformation or avoid this transformation, right. So, these are displacive, that is the characteristics of a displacive transformation, whereas the so called nucleation and growth type of phenomena is refers to here as a reconstructive transformation. Okay. So, that is a kind of terminology. Normally ceramists use these two terminologies, displacive transformation and reconstructive transformation, whereas metallurgists use diffusionless transformation or athermal transformation and isothermal transformation. So, that is the basic difference. Maybe we will discuss these things at a later stage when we talk about phase transformations. So, silica is a very unique system that way, where many displacive transformations takes place as well as some reconstructive transformation takes place. Two reconstructive transformation takes place which are time dependent, but these are other transformations are time independent, and they are not, as I mentioned few minutes back, that they are not always equilibrium transformation. Some non-equilibrium transformations also take place. These transformations do not take place until and unless you heat it to high temperature and then cool it back. Okay. For example, if you try to heat it to a very high temperature crystallite, sometimes depending on the rate of cooling, either it goes to the low crystallite phase or it can go to the low tridymite phase, right. So, there are some glass formations also, as you know. Silica is one oxide which is easily forms glass. So, once it forms a glass, then of course again the transformation becomes non-equilibrium transformations, and then depending on the cooling rate, depending on the other impurities present, many different cases situations may arise. So, otherwise these are the phases present in silica, and you get different kind of transformations as well at different temperatures. So, that is all so far as silica transformation is concerned. Keeping this in mind, we have some structures. These structures are to start with low quartz and high quartz. Low temperature form of the quartz, this is the low temperature form of the quartz, and on the left you have high temperature form of the quartz. Okay. So, the basically a silica oxygen network. These are shaded differently because they are at different planes. Okay. They are not in the sheet only. Okay. This is only one section, and they have been given different shades because they are in the different depths, right. So, these are the kind of network. Okay. Only difference between this structure and this structure, you will see these are regular hexagon here. Okay. These are all regular hexagons, whereas here there is a slight deformation. Okay. There is no regular hexagon, it is more of a pentagon, and then so it is a combination of tetrahedron triangles and pentagons. So, there is a distortion, and if you want to change this to this, is actually slight displacement of the individual atoms, and that is why this transformation is quite easy. At a particular temperature, suddenly the atomic positions change, but not to a great distance. The atoms do not diffuse from over a longer distance. So, it is all within the interatomic spacing, the movements are all within the interatomic spacing, and that is why this is one of the examples of a displacive transformation. Okay. So, it is much easy. So, and none of these displacive transformations are very easy to stop or quench the transformation. If it is a reconstructive transformation, nucleation and growth phenomena, then if you quench them very fast, or if you can change the temperature particularly from high temperature to low temperature, the transformation can be or the phase can be quenched. That means a high temperature phase can be available at room temperature because the kinetics is slow. So, you are not allowing, by quenching it fast or rapidly cooling it, you are not allowing enough time for the atoms to move, and therefore, the high temperature phase can be available at the room temperature or at lower temperature, although it is not a thermodynamically stable situation. However, any displacive transformation which do not take or do not involve so much of larger distance movement of the atoms, then you cannot quench it. You cannot quench it. So, even if at a very rapid heating or rapid cooling, the transformation will take place, and that happens when this particular situation between alpha and beta quartz transformation. And as you can see, the changes in the structure is only nominal. This is the cristobalite structure. Cristobalite has the most symmetric structure. As you can see, it is the highest temperature. Cristobalite is available at the highest temperature, and normally higher is the temperature or higher is the temperature of stability of any particular phase, that has a more symmetric structure than the lower temperature phases. So, the cristobalite has a highest temperature phase in the system, crystalline phase particularly, and it has the most symmetric structure, having the cubic symmetry. Okay. So, quartz does not have a cubic symmetry, it is a very complex structure, whereas if you talk about cristobalite, it has a cubic symmetry. However, one has to find one difference between whatever structures we have discussed so far. Whenever you are talking about the symmetry, it is the position of one particular atom, either the cation or the anion that dominates, that determines the symmetry. Here the symmetry or the motif here, what we call a motif, the units are actually tetrahedrons, silicon oxygen tetrahedrons. Those are the motifs of this symmetry, and the corners, in earlier we have discussed in many structures where the atoms are positioned in the corners of the cube. Okay. Here is a group of atoms is positioned at this corner of the cube. So, each corner is occupied by a silicon oxygen tetrahedron, not by silicon or not by only silicon or only oxygen. It is a tetrahedron which is occupied or sitting at each of the corners as well as the face centers. So, this is the face center, this is another face center. So, in all there will be 8 and 6, 16, 14 tetrahedra forms the face center cubic structure. So, this is a unique situation so far as the structure of compounds or inorganic compounds are concerned, whereas at least whatever we will discuss under this course. So, cristobalite has a close packed cubic structure, FCC structure, but the motif here is not single atoms, but it is the tetrahedrons. So, these are the details of the atoms here, once again with the framework of a cubic structure. So, at each corner you have 4 different ions, one is silicon ion, and surrounding it there are 4 oxygen ions. So, that becomes repeating force, a repeating unit in this structure. Okay. So, that is the description of the cristobalite form of silica. This is not a pure silica, of course, it is another structure. It is mullite. Mullite is the chemical formula of mullite is 3Al2O3 2SiO2. This is a silicate, and it has also its own structure. It is not related to Al2O3 structure, not to SiO2 structure, but is a completely different structure with distribution of silicon and oxygen, as well as silicon and aluminum, and this is what is the structure. This is also a you can see the crystal structure of mullite viewed along, there is a mistake over the 2 alongs, the short z axis. These are the lattice parameters A, B, C. Okay. You can see here A and B are same, more or less almost same, whereas C is different. So, it is a kind of tetragonal symmetry. The sides OC and T are never fully occupied. So, this is an idealized schematic of this orthorhombic or orthosilicate. Okay. This is called orthorhombic orthosilicate. So, these are the orthorhombic structure, and the chains of the octahedron at the corners and the centers lie along z axis. So, this is again the symmetry is through a group of atoms. Okay. The tetrahedron and the octahedrons are also there. Okay. So, this is the mullite structure, which is a very important compound whenever you are talking about any aluminosilicate heated to any aluminosilicate when heated to high temperature, for example, a kaolinite structure. Okay. Kaolinite is a hydrated aluminosilicate. So, at high temperature hydroxyl ion goes away, and what is remained is about is alumina and SiO2, and they form some compounds, silicates of this nature. So, mullite is one of the very important phases. Whenever any silicate structure is heated to high temperature, mullite is normally formed, okay, and it has a needle like morphology. Well, so far we have discussed different kind of silicates. Let us try to look at it in a unified manner. Here we have on the left the different kind of silicates, different type of silicates whatever we have discussed so far. The orthosilicates, that is the isolated silicon oxygen tetrahedra, that is orthosilicate, and then we have ring silicates, chain silicates, sheet silicates, and finally framework silicates, okay, or framework silicate structure. Now, these are some of the examples of orthosilicate. Forsterite, the mineralogical name of is forsterite, and the formula is this Mg2SiO4. This is the unit of SiO4, and it has 4 minus. So, Mg2 two cations have been added to satisfy the charges. Similarly, there is other silicates like phyalite, and then these are the mineralogical names of all these silicates listed here. So, phyalite is FeSiO4. This is again a very important compound, very low melting compound. Many of the refractories do have this particular mineral, and in fact, the presence of such minerals is always detrimental to the refractory property of the industrial refractories, because it has a relatively more low melting point. Montisilite is another kind of silicate. It is a complex silicate. As you can see here, 2 MgO, 2 Mg is satisfying the 4 charges, whereas here 1 calcium and another magnesium, 2 together satisfies the 4 negative charges of SiO4. Okay. So, this is another kind of mixed silicate, calcium magnesium silicate. Another mixed silicate is here, calcium iron silicate. Okay. Both of them has 2 charges or bivalent. In this case, Fe is ferrous, Fe2 plus, okay. It is not Fe3 plus. So, these are the examples of orthosilicates, and many of them do appear in association with other phases. In fact, phosphorite as such is a very good magnesium silicate, it is a very good compound which has a very important insulating property, and many of the insulators, good insulators, do have a phosphorite, and part of phosphorite Mg is added so that this particular phase is formed, and they have a good dielectric property also. Ring silicates, the examples are beryl, that is again the mineralogical name, and the formula is beryllium aluminum silicate. Okay. Beryllium aluminum silicate is a 6 member ring, because you have Si6, Si6O18. So, it is a 6 member ring, and beryl is a very important group of 6 member of the 6 member ring family of silicates. Okay. And cordierite, the next one is cordierite, once again is a ring silicate, and here you can see there are aluminum, part of the silica, you see Si6O18, in that you see again a 6 member ring, and part of it has been replaced by aluminum, and then it has been other cations have been added. Okay. So, it has become Si5, Si5. So, one silicon has been replaced by aluminum, and in fact, aluminum is one of the cations, although most of the time it has a octahedral coordination that we have seen earlier. Even the corundum, in corundum structure aluminum has a 6-fold coordination, but in silicates, many of the silicates, when the association with silicon and oxygen network, aluminum actually part of the aluminums goes to the tetrahedral site as well, replacing silicon. So, aluminum has a kind of dual character, it can go to the octahedral site, also it can go to the tetrahedral site, and that is one of the important features of many of the silicate structures. So, here that is what is happening. So, that is the cordierite structure. Now, cordierite is once again a very important compound in the family of ceramics. In whenever ceramics are used, mostly in high temperatures. So, if you are heating a ceramics from room temperature to high temperature, it will always go through some thermal expansion, because all materials have some kind of a thermal expansion property. Some of them have a very high thermal expansion coefficient, others may not have that kind of coefficient. So, if you are talking about a high temperature material, in most of the applications one would like that the thermal expansion coefficient is low, so that there is not much of volume change or geometric change of geometry or the volume change during its heating or cooling, because during heating or cooling and if there is a sufficient amount of volume change, then there is a possibility of breakage, there is a possibility of crack formation, and the material will lose its integrity. Therefore, in many applications where the materials have to be heated several times or cooled several times, for example, in furnaces, there are many products where in fact all ceramics have to be heated to high temperature, and it has to be supported on some material and some what we call kiln furniture. So, inside a large kilns you have some kind of a supporting system on which the actual products are kept, and so they have to be used large number of times, repeatedly used inside the furnace. So, they have to be heated and cooled several times. If the material has a very high thermal expansion coefficient, then there is a possibility of crack, and the life of the material will the life of the supporting system will be very poor or very low, and therefore, it involves a lot of expenditure. So, this kiln furnitures are all made of mostly kiln furnitures are made of cordierite ceramics. Cordierite is the phase which has a very low thermal expansion coefficient. Compared to many other materials, cordierite has a very low thermal expansion coefficient, and therefore, it is a very ideally suited for what we call the kiln furnitures, okay, which is actually used to support the other ceramic products which are of interest to us. So, cordierite, that is why is a very important ceramics, and one needs to know its structure as well as property. Maybe if time permits, we discuss why the cordierite ceramics do have a very low thermal expansion coefficient. Okay. Now, we have then chain silicates, ring silicates, and then this chain silicate. This is another magnesium silicate. It is this one, phosphorite was 2 MgO SiO2. Here it is, that means 2 molecules of MgO is forming a compound with 1 molecule of SiO2, whereas here 1 MgO and 1 SiO2, that is MgO SiO2. Okay, so that is enstatite, and that has a different structure, compared to phosphorite. Both of them are basically magnesium silicate, but they have a different structure. This is also another one. Here also you have a multisilite. You can see the multisilite here, which is calcium magnesium silicate. This is also a calcium magnesium silicate, but the formula is different and the mineralogical name is also different, okay, and the structure is also different. Okay. So, you can see the kind of the variation one can have in the silicate range of products, and their composition, their structures are quite different, although silica is the main building block of all these silicate materials. Then they have a seed silica or seed silicates. We have discussed little bit about the structure. muscovite, that is the potassium mica, and the structure, and you have always OH ion there. Okay. OH ion is one of the major constituents of all these seed silica. Any seed silica you have, always there will be a OH ion, whether it is muscovite, kaolinite, then talc. Talc is another very important mineral, which is has a soapy structure, is a fine form, and where from the name talcum powder came. So, the talc is basically a naturally occurring mineral and is a silicate structure, and these silicates are either have what we call a symmetric structure or asymmetric structure. Like kaolinite, as I discussed, is an asymmetric structure, one layer of silica and one layer of aluminum hydroxide, whereas the muscovite is basically a symmetric structure with one layer of silicon oxygen, another layer of two layers of silicon oxygen, and in between you have a layer of aluminum hydroxide. So, these are talc, magnesium, basically hydrated magnesium silicate, that is talc. Kaolinite is hydrated aluminum silicate, and this is symmetric structure, one layer of silica and one layer of aluminum hydroxide. Here 2 layer of silica and 1 layer of magnesia. Instead of aluminum, if you put magnesium in a very similar structure. So, just replace aluminum by magnesium, you will get talc. And then these are biotite, these are mica based or mica like substances, and muscovite is actually mica. Framework silicates. When you talk about framework silicates, you know, in a seed silicate, if you hierarchically you can when you go from orthosilicate to seed silicate, the basic difference is here there is no bridging oxygen, that means there is no oxygen which is connected between two silicon ions. Here ring silicon, 2 of them is connected, and then if you have chain silicates, you have 2 or 3, both are possible, and then sheet silicates, 3 of the oxygen ions are shared by silicon, only one oxygen is available to be connected or to be bonded with other cations. In this case, in a framework, all the silicon, all the oxygen are basically with silicon, all the oxygens are shared between silicon, and that is why you have a pure silicate structure. Okay. You have a pure silicate structure, silica structure, in which there is no other cation. However, very similar things also can happen with other structure, other compounds like feldspar, sodium, aluminum, silicon, oxygen. Okay. Sodium, aluminum, in fact, in these cases what happens, why the other cations, how the other cations comes in, because silicon, a part of the silicon has been replaced by aluminum. Okay. Silicon has a 4 tetravalency or 4 charges, 4 positive charges, whereas the aluminum has only 3 positive charges. So, it has one less positive charge. To satisfy that charge, another extra positive charge has to come in from the alkali ion, and that is why this sodium and aluminum, as if sodium and aluminum together is replacing one of the silicon. So, otherwise it is basically a silica structure. All the oxygen ions, are basically shared by silicon atoms or silicon ions, but because one of the silicon ion has been replaced by aluminum, and aluminum in this case goes to the tetrahedral site. So, to compensate for the charge imbalance, one sodium ion has to come in, and that is how a feldspar structure is created or feldspar compound is created. It is basically a framework, what we call a framework silicate, right. And as we have mentioned earlier, feldspar is one of the basic ingredients of whiteware family of ceramics or porcelain family of ceramics. It has a relatively low melting point and acts as a flux, forms a viscous liquid or viscous glass that acts as a binder for the other ceramic particles, particularly quartz and mullite and so on. Okay. So, feldspar is a very important ingredient of whiteware family of porcelain ceramic. Same is the case with zeolites. Zeolites, as you know, is a very important for many different purposes, once again because of its crystal structure. We will not be discussing much about these things, so I am spending little time on this. Once again, it has a framework structure, and some of the silicon has been replaced by aluminum, sodium has been added, and in addition you have some hydroxyl ions also. Okay. So, in this case zeolite forms, and one of the major characteristics, some important characteristics of zeolite is that it has, the structure is such that it has some crystallographic holes, crystallographic channels, okay, very fine channels in the level of angstroms, and that makes becomes useful for many purposes, including catalyst. Many of the zeolites are good catalyst or catalyst carriers, and in very recent times these channels are very fine channels or crystallographic channels, or they are very uniform channels, and through these channels one can pass through many different gases. So, either they can pass through or they can get absorbed. So, zeolites are sometimes or many times used for adsorption purposes. These fine pores or fine crystallographic channels are used for adsorption of different other molecules. Maybe some of the gaseous molecules can be adsorbed by this surface. There are many different forms of zeolites, so where these channels can be controlled because of the crystallographic nature or change in the crystallography, and therefore one can adsorb different gases. For gas separation one can use them. Even gas separation can be by 2 different techniques. One is adsorption, you are just removing the gas and getting adsorbed in this micro holes or micropores of the zeolites, that is, so it is getting absorbed there, or sometimes it can be used as a membrane, a semi-permeable membrane. So, through these channels particular molecules of gaseous molecules can pass through, the others may not pass through, because if provided the molecular size of those gases are bigger than the channel size. So, they can be used as semi-permeable membranes, and in the context of new generation of fuels or hydrogen economy, where hydrogen separation or hydrogen generation is very important, or hydrogen separation from other hydrocarbons or other gas mixtures are important. There is an attempt to make these zeolites to be used as semi-permeable membrane, where hydrogen can pass through because it has a very small molecular size, whereas hydrocarbon or some carbon dioxide may not pass through. So, if you have a mixture of carbon dioxide and hydrogen made from cracking of hydrocarbons, one can generate hydrogen and separate out hydrogen and carbon dioxide, so that hydrogen can be separated in this manner. So, zeolites having a very peculiar or very important crystal structures, having their pore sizes or channel sizes which can be adjusted by changing the composition and the structure, one can use it for many different industrial purposes. So, zeolites is another good or important member of the silicate family, and the last one is anorthite, is calcium aluminum silicate. All of them, as you can see, aluminum is one of the ions present particularly to replace silicon, and accordingly other cations also come in to satisfy the charge imbalance. So, this is the in short the summary of different kind of silicates and their structures, and also I have discussed some of the usefulness of many of these compounds. Well, so far we have been discussing about the structures of different oxides, but oxides are not the only group of compounds which will be useful for our later discussion or further discussion, so far as their functional properties and their mechanical properties are concerned. So, many of them, particularly the advanced ceramic group of compounds, are not non-oxides, or they may be carbides, nitrides, borides and so on. So, here there are few examples of non-oxide group family of ceramics. To start with is the titanium diboride. It is again useful, we will come across these compounds later on. So, let us just have a look at it, what is the structure of them. This has a hexagonal crystal structure and hexagonal structure, if you remember just now a few minutes back I discussed that one of the angles is 120 degree, and that is what is shown here. So, the open circles are actually titanium ions which are larger here compared to the boron. In all oxide structures we have seen that the cation has a smaller size and oxygen is a larger size. Here actually both of them in a sense are cations, and they do form compounds, but their ionicity is very similar, and therefore, they do not form ionic compounds, they form mostly covalent compounds. And so, the ionic sizes are also of different nature. Titanium, when you are talking about titanates, titanium is a much smaller ion compared to oxygen, and here if you find that boron is still finer, still smaller compared to titanium, right. So, these are the titanium ions in the form of a cube, whereas boron ions forms another layer in the form of a hexagon. So, that is the description of titanium diboride. So, hexagon basic symmetry becomes hexagonal crystal. Okay. So, these are some of the positions of the boron atoms, how they are distributed, and the distribution of the titanium. So, that is the brief description of what we know about the titanium diboride. Another compound we have discussed, we have mentioned it about discussing about the woodizide structure or zinc blende structure. So, there we have hexagonal structure as well as cubic structure, both are possible. In fact, silicon carbide is a very important group of advanced ceramic materials, and it has a very good high temperature mechanical strength, and it has been used extensively for many different purposes. We will discuss them later. But silicon carbide, this is a typical structure, but one has to remember that silicon carbide has a many different structure types. Okay. There are polytypes, there are different kind of polytypes we call. We will discuss more of them in details, what are the different kind of structures available, and what are the relationship between different structures. So, silicon carbide has many different structures or many different atomic arrangements, and accordingly different properties, at least alpha silicon carbide, beta silicon carbide, and so on. So, we will discuss some of them later on and also their properties. But one thing here you have to remember, carbon atoms are much smaller atoms compared to silicon, even compared to silicon, carbon atoms are much smaller, and they goes to the interstitial sites. Now, these are, one is the interstitial sites, and these interstitial sites are little, or the size of the carbon atoms may be slightly bigger than the actual interstitial sites available in the silicon arrangement. So, we will discuss that later on, how exactly the carbon atom goes into the interstitial sites and form the silicon carbide structure. This is a little complex structure of silicon nitride Si3 and 4. Once again, this is also an intermetallic compound, some kind of an intermetallic covalent compound in fact, and it has also many different properties. It is a good insulator at high temperature, and it has good fracture toughness. So, this is some of the description, the details are not there, but you can see this is sorry. This is a simple description of silicon and nitrogen. The white ones are nitrogen and the bigger ones are the silicon. Once again you can see the silicon, which is the metal ion, has a larger size than the nitrogen. This is more or less a cubic symmetry. This is another non-oxide ceramics, molybdenum disilicide, molybdenum and silicon. Here again the size difference is different. Molybdenum has a larger size than silicon. Okay. So, molybdenum goes to the center of the cube as well as the corner of the cube, and silicon goes in between the interstitial sites. These are interstitial sites within the structure of cubic structure of molybdenum. Molybdenum disilicate is a very important industrial application. This is one material. In fact, like silicon carbide is a semiconducting material. Some form of silicon carbide has a good semiconducting property, and in fact it has been used as a high temperature semiconductor. So, the electrical properties of many of these non-oxide group of ceramics are quite interesting, and in that context molybdenum silicide disilicide has a fairly large conductivity, but not like fully conductors like metallic conductors, but it has some resistance but fairly conductive. So, both silicon carbide and molybdenum disilicide they have similar property in that respect, so far as the conductivity is concerned, and they can be used as in fact they are extensively used as heating elements of different furnaces. Many of the furnaces, the basic principle of heating a furnace is basically a joule heating. That means you pass some current through these materials and there is a IR, I square R heating. Okay. So, current square into resistance. So, these ceramic materials, because they have a high melting point and also have a fairly low resistance. So, you can pass fairly large current through this, and as a result they will heat up. So, these are the heating elements of different furnaces. Silicon carbide can be used up to a temperature about 1400 to 1500 degrees centigrade, whereas if you still need a higher temperature, molybdenum disilicide is the answer. So, most of the laboratory furnaces or even industrial furnaces, if you want to go beyond 1500 degrees centigrade up to about 17 or 1800 in some cases. So, molybdenum disilicide is used as the heating element. So, that is the importance of molybdenum disilicide. So, it has a very good high temperature mechanical property as well as electrical property, right. So, this has a tetragonal symmetry and MoSi2 with molybdenum occupying the corner and the body lattice positions are occupied by the silicon. Okay, I think that completes our discussion on crystal structures. We have discussed fairly large variety of compounds from oxides to silicates to non-oxides, some carbides, nitrides, silicide, borides. So, all of them have been touched upon, and a brief discussion on the crystal structures we have gone through. That ends our discussion on crystal structure. Next time, the next class we will be discussing about the crystalline imperfections, because we have discussed so far about the ideal structures, but in practice or in reality the structures are really not ideal. Many positions of the structure are occupied by either vacancies are there, or interstitials or impurities. So, we have to understand what is their role when there is particular atom is missing or an extra atom is there within the structure, either of the same material or from a different material. So, that is what we call the atomic imperfections or crystalline imperfections, and we will discuss them in the next class. Thank you.